Large language models, or LLMs, have shown impressive abilities in generating code, but there's still a noticeable gap in performance between open-source models and closed-source ones like those from big tech companies. This research paper, titled Data-Efficient LLM Fine-Tuning for Code Generation, is led by YGLV from Nanjing University of Aeronautics and Astronautics, with corresponding authors Zhan Xia from the Shenzhen Institute of Artificial Intelligence and Robotics for Society, and Shengjun Huang from Nanjing University. The paper focuses on making the training process for these models more efficient by carefully selecting high-quality data and optimizing how that data is processed. The core idea is to fine-tune LLMs for code generation without needing massive amounts of data, which can be time-consuming and resource-intensive. Traditionally, researchers generate large volumes of synthetic code data using powerful models like GPT-4 to improve open-source LLMs such as DeepSeek Coder or Code Llama. However, this often includes a lot of low-quality data, leading to inefficient training. The authors argue that it's not about having more data, but about having the right data. They draw from recent studies that show high-quality, carefully chosen samples can outperform vast datasets. In the introduction, the paper highlights how LLMs like Codex have revolutionized code-related tasks, powering tools such as GitHub Copilot. Yet, open-source models lag behind closed-source ones due to differences in training data scale and quality. Scaling laws in AI research suggest that bigger datasets help, but only if the data is good. For instance, a study called Lima demonstrated that just 1,000 well-curated samples could achieve excellent results, emphasizing quality over quantity. To address this, the researchers propose a data selection strategy that prioritizes both the complexity of the data and its alignment with the original dataset's distribution. They start by using the k-means clustering algorithm, which groups similar data points in the dataset. This ensures that the selected subset maintains a distribution similar to the full dataset, preventing any bias or imbalance that could hurt the model's performance. Once the data is clustered, they evaluate the complexity of each sample using something called the Instruction Following Difficulty, or IFD, score. This score measures how intricate a programming problem is, based on factors like the need for advanced reasoning or integration of multiple knowledge areas. For each cluster, they select the sample with the highest IFD score, meaning they pick the most challenging and potentially most valuable examples. This approach allows them to create a smaller, high-quality subset that still represents the overall dataset effectively. In addition to data selection, the paper introduces a technique called dynamic pack for optimizing the tokenization process. Tokenization is the step where text is broken down into tokens that the model can process, but in practice, batches of data often include padding tokens to make everything the same length, which wastes computational resources. The dynamic pack method fixes this by sorting the data samples in each batch by their length and then concatenating them in a way that maximizes the use of the model's context length without exceeding it. This minimizes padding, reducing unnecessary computations and making training faster and more efficient. The experimental results demonstrate the effectiveness of these methods. For example, when fine-tuning the DeepSeek Coder-based 6.7b model on just 40% of the OSS-Instruct dataset using their strategy, the model achieved an average performance of 66.9%, which is actually better than the 66.1% performance when trained on the full dataset. Moreover, the training time dropped from 47 minutes to 34 minutes for a single epoch, and peak GPU memory usage decreased from 61.47 GB to 42.72 GB. Similar gains were seen with the Code Llama Python 7b model on the Evol-Instruct dataset, showing consistent improvements in both performance and efficiency. This work underscores the importance of thoughtful data handling in LLM training. By focusing on complex, representative samples and streamlining tokenization, the authors not only enhance the model's ability to generate code but also make the entire process more practical for researchers and developers with limited resources. The code for this approach is available on GitHub, encouraging further experimentation and adoption in the community. Overall, these innovations could help bridge the performance gap between open-source and closed-source models, making advanced code generation more accessible. The paper's index terms include large language models, code generation, and data selection with tokenization, reflecting its key contributions to the field.